before we proceed any further, let me show you some 3D visualization which will help you understand what's going on in the complex plane. So what you're looking at the projection is the relief of the real part of the exponent function. So let me rotate it for you. And the blue line corresponds to the initial position of the contour, which is a real axis. So the idea of the steepest descent method is to shift the contour in such a way that it glides along the lowest regions of the relief of the real part of the exponent function. So like this. And as you probably notice, it is obvious from the picture, indeed, once you draw the contours through the saddle, then indeed it occupies the optimal position, the lowest possible position on the relief of this real part of the exponent function. Now let's proceed further. So since we discovered the position of our saddle point and the steepest descent direction, the next step is to expand our exponent function near the saddle. As you remember, the expansion should be aborted at quadratic terms, but here the full function is quadratic. So this expression is in fact just the exact expression of the function. So let's introduce the new more suitable complex variable v as follows. And the exponent function is now rewritten as follows. Well, in fact, you can detach here a full square. And the first term simply becomes the new complex variable v. Let's see what's going to happen with their pre-exponential function. Let's denote it as g of t. And we plug in this decomposition. So the pre-exponential is turned into ix plus I plus v. Now, once we plug in this expansion into our original integrand, what we notice immediately is that our exponent function, exponential function, is transformed as follows. So some independent of v part is detached, and the part which is responsible for the convergence is as follows. And now we see that the important v important for the convergence of the integral v are of the order of 1. Notice the absence of the large parameter in front of this exponent function. However, now the large parameter enters our pre-exponential function here, ix. So despite the fact that our regions of convergence is not small now, it's of the order of 1, we still can simplify our pre-exponential function and reduce initial complicated integral into a Gaussian one, which corresponds to the logic of the steepest descent direction philosophy. So our g of t function now can be simplified because we can drop I term, which is of the order of 1, and v in comparing to this large ix term. And now the integral is reduced to a simple Gaussian one. Again, no large parameter in the exponent, and the resulting answer is the square root of 2 pi. Now we are ready to discuss the case of large and negative values of x.